Hello. In this video, we're going to be going over the rate function. The rate function is used to calculate the interest rate for an annuity based on the term, the payment, and the outstanding balance. Before we get there, though, let's just see how this relates to the payment function that we know from our earlier exercises. So what I have set up here right now is that we have a term of a loan, its annual rate, and the outstanding balance. So just like you've done before, you can use the payment function, or PMT, to calculate the payment that would be required to pay this loan off over time. So we can take our rate, remember, and divide by 12 to get that to monthly. We can reference our number of periods, and then the negative of the outstanding balance, and that gives us our payment. In this case, $530.33 will pay off this loan in 120 equal payments over time. So now let's see how we would use the rate function and the payment function applied to a normal bond. Now, bonds are different, corporate bonds and government bonds, from traditional amortizing loans. When we think about a mortgage, that's a loan that you're going to pay off over time, and you're paying the principal off in each payment over time. In contrast, most corporate and government bonds work where you pay the entire principal back all at the end. So in between, when you make those interest payments, they're really interest only over time. So we need to account for that when we set up our formula. So first, let's see how we do that in payment, which we've actually seen before. So we can use payment here, and we can use our rate. So we're just going to assume an annual bond to start out here. We'll change that in a second. Number of periods, 10. Our present value, well, that's going to be the negative of the market value, or whatever you pay for this bond. So this is your initial outflow to buy the bond. And then when it pays back in the future value is that par value, or we also call it the face value. So once we plug that all in, we see that the payment on this bond is $35 a year, which makes sense because that's 3.5% of our $1,000 par value, or face value. So that's the simple way we calculate a payment. So now let's see how we'd actually apply that to the rate formula. So just like in the prior example, we're going to use the inputs we had, and we're going to use our payment that we calculated as well. So let's set up our term equal to what we had before, our 10 years. Our coupon payment, now we could either reference the $35 we calculated, that's one option, or we could recognize that the coupon payment is simply the rate times the par value, or the face value of the bond. So that same $35. The par value is the $1,000 we're given. The market value will take us $1,000. And now we can use our rate formula. In per, right, we still have 10 periods like before. Our payment we calculated, same as in the prior example. Now here it gets a little different. What do we use for the present value versus what do we use for the future value? So the present value is what you pay for it. So here we're going to put negative with that market value, or price. Then we can put the future value as the par value of what you're going to be paid back at the maturity of this bond. So once we plug all those variables in, we get that our rate is 3.5%. So now let's actually test the model to see if it's working the right way. Because one thing we should develop is some intuition around what happens when prices change. What changes to your rate that the bond is paying you, right? The rate function here tells you that you're earning 3.5% on this. So if instead of paying $1,000, let's say we pay $900 for this bond. Well, we're going to pay less today, which means, and we're getting the same cash flows in the future, which means we should be earning a higher return. So if we put this in, we see, yes, now we're earning 4.78%. However, if we pay more than face value for the bond, say we pay $1,100, we're putting more money out today, getting the same cash flows in the future, so we must be earning a lower return because we paid more today. We can verify that and see that, yes, now we earn 2.37% as our rate that we earn here. All right, so in this example, and let me just set it back to par, where we see 3.5%, this assumes that all the coupons are happening annually. You're getting one payment per year. Now next, let's look at an example where we get semi-annual payments, which again is customary when we see corporate bonds, treasury bonds, etc. All right, so just like in the previous example, we can reuse our parameters. So here I'm just going to link back to our main parameter inputs. Our coupon payment we can just take as our rate times our par value. Par value we can link back up to the top. Market price will link up as well. And now we're going to calculate a semi-annual rate. So everything I've done before in this line is typical of what you see when you're given data on a bond. You have to know that bonds pay semi-annual interest. So this $35 coupon payment isn't actually ever a $35 payment. It's going to be half of that every 6 months. So we need to adjust for that in our rate function, just like we've adjusted from annual to monthly in previous examples. So here, as we adjust our formula, our number of periods is going to have to be the years times 2. We multiply by 2 because that accounts for the semi-annual payments. Our payment is then that $35 a year divided by 2. So we have twice as many payments, but they're half as much. Our present value is still the opposite of whatever our market value is that we pay for it. And our future value is still that face value or that par of 1,000. Now we get a semi-annual rate, right? Which again, we need to annualize to make that comparable. So to get the APR on that, we can just multiply it by 2. And this rate, or this APR, based on our semi-annual payments, is also what we call the yield to maturity. That's the yield that you're going to earn if you bought this bond at 1,000 and you held it to maturity and received all the cash flows from it. So that is exactly what we're calculating when we use the rate function, is we're getting that yield to maturity on a bond. Now let's look at a final example where we actually use real bond data. So this is data similar to what you'll see in your assignments. And so we have to figure out how to deal with this data and adjust the rate formula to actually handle real world data. Because in the real world, often, for example, you'll have a maturity date when that bond pays off, and you'll have the current date. So conveniently, I'm setting this up to where the current date is right after we've received our most recent payment. This function is not going to work very well if you're in between periods. If you're 3 months away from a coupon payment, the rate function is not going to work as well for us. There you just kind of got to model out the cash flows and take exactly the number of days until each payment into account, which you can build with a more fully fledged, built out financial model. Here, the rate function is going to be handy for us because we can basically use it because we're on those kind of semi-annual dates. So let's see the couple adjustments we have to handle to use this real world data. So the first thing we have to do is adjust for the fact that we don't know how many payments we're dealing with. So one way we can do that is we can take our maturity date minus our current date. So we can figure out how many days we have from now until that final cash flow we get. So if we do that, we see a big number, 5,296. That's expressed as days. So we want to translate that to years. There are a couple different conventions for doing this, and we're not going to get into the details. We're just going to assume that 365 days is what we're going to use as our denominator. Some bonds deal and quote in kind of 30 to 330 days a month, 360 days a year, the 3360 convention. Some do actual number of days and actual number of days in a year, so they're going to change with things like leap years. It just depends on what bond and what market you're dealing with, how they quote these yields to maturity, and how they calculate the time to maturity as well. We're going to keep it simple and just divide by 365 days for this class. All right, so there you see that we have 14.51 years to maturity. Now, once we have that, now we have a term, so we can actually use our rate function. We'll do our number of periods, 14.51. Our rate, or our payment rather, well, we can use our coupon here. But now we have to look at our data and realize that that coupon payment doesn't necessarily line up with our price, because we're not getting $3.03 for every 98 cents that we put in. Instead, that 3.032 is stated as a percent. So if we want it to translate to kind of to match our price, we just got to divide by 100. And there's really no good way or solid rule of thumb on how you're going to always do this. You have to look at your data and make sense of it. In this case, we recognize that the coupon is way too big to be an actual dollar figure. We're going to assume it's percent and divide by 100. Now our present value, what did we pay for it? Well, there's our price. And our par value right now is just stated as $1. right? Typically this is $1,000, but again, it depends on the bond and how they're quoting the price. We can assume pretty safely that it's not a $1,000 bond that costs 98 cents. That could happen, it's just not very likely. What's more likely is it's a $1,000 bond that costs $983.44. They're just quoting it as of a dollar being the full par value. And we're going to show you how to handle this kind of by adjusting the data in just a second. All right, so we got our rate function. We run that and we see our yield to maturity is 3.17%, which is a little bit higher than our coupon. Right? So whenever we get a yield to maturity, we want to compare it to the coupon and see if it makes sense. So the coupon is just a little over 3%. The yield to maturity is 3.17%. Now that can only be the case that you're actually getting a higher yield than the coupon they're paying you for, paying to you, if you actually paid less than the face value for the bond. And that's exactly what we see here. You actually paid a discount for the bond. You only paid about 98 cents for every dollar. So because you paid less, that's why you're earning a higher return. Now, if you don't want to have to make adjustments in the rate function itself, like we did over here, you can also just adjust your data. So let's see how we do that. So for example, I can just take this data, let's take the current date, and let's go ahead and make the coupon adjustment here. All right, I'm going to divide by 100 to get that 3.03%. I'll take my maturity date, my price, and my par value, the same as my inputs. Our yield to maturity calculation is going to be the same. And now our rate function. Now we don't have to make adjustments here. We can use our years to maturity. Our rate, we've already adjusted to actually be a percentage. Our present value, we put a negative on. And our par value is our future value. And we get the same 3.1762% answer. So really, either of these two lines, they get the same answer. It's just how you want to organize your data. Some people like handling the adjustment in the rate calculation. Others like making the data a little bit more clear to work with, and then make the rate function as simple as possible. One last way to do it is actually to go up to the true par value of this bond, which is likely $1,000. So let's do the same thing we just did. I'm going to come over here. I'm going to go a little bit out of order. Let's take our par value times 1,000. Let's take our price then times 1,000. So we're scaling everything up. We're going to keep our maturity date. Again, I'm linking to those input cells. And now for the coupon, well, we can take the fact that we have a 3.03% rate, multiply that by our par value, and get $30.32 as that coupon. So this looks much more like what a normal bond would actually pay and how it would be actually priced in the market. Our last step is to copy our yield years to maturity. And finally, the yield to maturity, well, we can just copy that formula down. Because all we've done here is scaled everything up by 1,000. So whether you want to deal in $1 increments or $1,000 increments, as long as the numbers are relatively consistent, you're going to get the same answer as far as the yield to maturity. Now again, the final thing to note here is that this calculation was all done assuming that we're at a point where we have just received the last cash flow. So our first cash flow is 6 months off, then 6 months after that, and on down the line. If that's not the case, the timing gets a little bit different, and our yield to maturity calculation is going to get a little bit more complicated as well. We can't use the rate function anymore, but for this class, we're going to assume that you can go ahead and use that rate function. Whenever we're counting the time to maturity, you can just take the difference between the maturity date and the current date, and then divide by 365. That will give you the number of years to use for your in-per parameter. Then you just have to make sure you get the right coupon, price, and par value of the bond.